Hi, this is our introduction to physical geography, and we're going to be using these notes and much of nature and society to understand the physical environment. And I am going to be just restricting this to YouTube. So basically, you can kind of use this as you would in a classroom setting where the instructor is writing notes on the board. So what you see right now, for example, you would write as part of your notes, okay? And the nice thing about this, I can't get ahead of you because you can literally stop this any moment you want, but in class you can't. So there are a few advantages of this. The disadvantage, of course, is it's not quite so easy to ask a Q&A right off, but always send me an email if you have a question on something. Happy to, or during my office hours or whenever, and we'll talk about it if you want. Okay, so let's have a look at this presentation. So there are the spheres of the Earth, and usually we talk about four of them. And as you look at this, some of those are obvious. The biggest thing that you see there, if you're looking, is what? The biggest surface area. It's water, right? And of course, you see the clouds, you see what appears to be the greenery of the Earth, and a very thin layer you might think of as the atmosphere where you see those clouds. And so what we have then, broadly speaking, is the hydrosphere, largest part of which, of course, is the oceans, but even the water content in the air could be that as well. The Great Lakes you can see way up here in this corner, the world's rivers. There's also water underground, so lots of water, the hydrosphere. The lithosphere is that surface crust of the Earth, and then down to some extent below, there's different definitions of that. But whether it's islands or whether it's continents and so on, we're talking about the Earth's crust, and to some extent below that. Of course, there's water in the lithosphere, so these are interconnected. And that's a theme I'm going to return to many times, the interconnectedness of all of this. The atmosphere, and in this case, we even have kind of cross-sectionally looking at the Earth, maybe on one margin or the other. Can't really see it, but when you think about how far it is across here, and then the atmosphere itself is only some dozens of miles thick, it's no wonder that it doesn't seem to have much of a depth perception in view there. The biosphere is the living part, and this is suggested by the green here. But in fact, there's lots of greenery even in these browner areas that imply places that are a little drier and so on. But the biosphere is a very big part of our story. And of course, it's supported by the hydrosphere, the lithosphere, and the atmosphere too. So again, the interconnectedness, really important. So latitude is something that I'll refer to from time to time, especially in the first units here where we talk about Earth-Sun relations. So kind of going back to maybe middle school where you might have picked this up first. So you have the equator, okay, which is really cutting the Earth in half. And any distance you go away from that, you are getting into lines of latitude greater than 0, whether we're going north this way or whether we're going south this way. And so key lines to know, I'm going to assume by the time we get to exam 1 that you'll know. When I say the Arctic Circle, you'll know I mean 66.5 degrees north, and the Antarctic Circle at the same latitude but in the southern hemisphere, so it's 66.5 degrees south. North and south poles at 90 degrees, and so on. And if you want to think of how do we come up with those degrees, imagine you're kind of in the center of the Earth, and so this line straight across is 0 degrees, okay? But if you think about this tropic here at 23.5 north, and actually that line is misdrawn a little bit, it should be down here a little farther, and 66.5 north, which is the Arctic Circle, and Antarctic Circle, the same latitude here. So you have those, okay? So the tropics, the Arctic and Antarctic Circle, the equator, and the North and South Pole, okay? So those are lines of latitude, and they're parallel. So the other thing to write down is that these are parallels, okay? And by the way, if you're one of those that you want to have your own copy of this to study easily without having to access the internet, you might also just put this on your phone or something. You can always take little snapshots. Not a bad idea if you don't want to write all that down. But it's probably a good exercise just to do that the first time, just to sort of know where they all are. All right. So we've talked a little bit about all of this already. So just kind of reviewing these again visually in print. 23.5 north and south are the tropics, okay? And later we're going to describe why they are located exactly those locations, okay? And then the Arctic and Antarctic circles. Together now with the concept of halfway between the equator and the North Pole, the equator being 0 and the North Pole being 90 degrees north is 45 degrees north. That's where we are in the Mid-Willamette Valley. So 45 degrees north is halfway between the equator and the North Pole. And you've probably seen this if you've been on I-5, a little bit north of Salem. You've probably seen this sign. Okay. So isoline mapping is something that you see a lot in physical geography, and we'll talk a bit about that in this class. So some examples, topographic maps are one, and the topographic maps are lines of equal elevation or colors showing a narrow range of elevations, okay? So there's a video to view here and learn about these various things, what contour lines are, how to tell steep areas from flatter ones, and what scale is 1 inch represents so many inches, given an example in the video, okay? So we'll come back to the videos in a moment, okay? So the second is isotherm maps, and therm kind of sounds like temperature, doesn't it? So that's one way to remember it. So isotherm maps are lines of equal temperature. So using this map, what is the approximate temperature within 2 degrees in the Puget Sound area, the coast on the Oregon-California border, and the California-Mexico border at the Ocean Beach, okay? So what I'm going to do, by the way, on these where there's videos embedded or maps, is I'm going to go ahead and just have you do that independently, and I will post this particular slide in, it will be posted in your course delivery system, Canvas, so you'll get a chance to do that. These are just kind of little learning modules that I'm going to have you do independently, okay? And then iso-HIAT maps, and I'm going to show you one of these. I'm going to show you one of each of these actually, but I just want to first review them, okay? So let's go to the topographic maps first, and we'll just have a peek at these, and then later you can figure out the answers to the questions, okay? So got kind of a slow delivery here. I'm not sure why this is slow. Let's cancel that for now. I may have to look that. Oh, here we go. Okay, it was just too slow. We're there. Now, this is a topographic map. And in that, you can see all these little lines, and there's kind of like a thicker lines and thinner ones, and those are just kind of real broad round numbers like 4,800 and 5,600 and so on, okay? And I'm going to zoom into that just a tiny bit. Let's see, we'll come down and look at that. And so this, if you look at it, these are glaciers, and the glaciers are flowing down into the White River and so on. And so there's a question or two about that in that, okay? So that's one. And then we'll go back to our outline and isotherm maps. That one came up much more quickly. That's nice. And so this shows isotherms for the North American continent on a particular day, June 10th, 2003. You want to know. And so this is the 80-degree isotherm. That means everything on this side of it is warmer than 80, and everything on the other side is cooler. So you can see that there's an interval of 5 degrees between these lines. And if you look at the Oregon coast, there'll be a question on that. You can see that the 70-degree isotherm extends right down to the southern Oregon coast there roughly, okay? And so it's a little cooler up there, but 70 right along that line, and a little warmer further south, okay? So that's the concept there. So, and then iso-HIAT maps are lines of equal precipitation, so let's have a quick look at that. This would be one of Hawaii, and in fact, a friend of mine was involved in creating this atlas. and I went to grad school with him. And this is, kind of zoom in a little bit, you can see that, wow, these are rainfall values for October. And you can see that the big numbers are up high here. You can see this basically is a mountain here. And this is millimeters. So that's about, that would be the equivalent of 7/10 of a meter if you want, or in other words, about 28 inches on average in 1 month. So this is a wet place, okay, up here, up high. So those are, on the other hand, very much drier on the lower elevations, especially on this side. And there's a reason for that. When we get into precipitation later, we'll find out things like that. All right, so this is kind of introducing these to you, okay? And then there's ISO bar maps, which are just lines of equal pressure, okay? I'm going to check our time here to see where we're at. Yeah, I think we're okay still. So looking at a geographic information system, it's just defined as any system in which can facilitate the analysis of multiple layers of spatial data. Now, spatial means geographic, okay? So these are maps of specific themes. So what we see here is a GIS system with different layers. Let's talk a little bit about each one. The layers include things like things that you might relate to, for example, kinds of soils, okay? Whether or not there's wetlands areas, okay? So some parts of the map would be wetlands. There's different elevations. So the topographic base map here would have different elevations on it. Zoning, in other words, what are the regulations about what can be done where on maps, okay? So if you look at all of this, then that could tell you from that map places where you could maybe build subdivisions for houses. You certainly wouldn't want to build them within the wetlands, and maybe bordering them, perhaps, depending on a lot of things. And so that zoning map then very often is created by a lot of analysis of the other layers of data and how they interact, okay? So that would be a simple GIS system. You can query it in a variety of ways. You can use a GIS system to figure out where a house would be at risk if there were a major earthquake from landslides. Some of that would have to do with slope, like the topographic base map, and then also maybe the kinds of soils that you might have in the area will give us some sense of whether they're going to be stable when there is a major earthquake. So let's pause this one here, and I apologize for the pause there. Somehow the actual timing sometimes falls off the screen. I can't tell where. So we'll start this up with the next video. Sorry about that.